I learned the cosine law in grade 10, but, like the Pythagorean theorem before it, I was never taught why it is true. It turns out that the earliest known proof of the cosine law was written by Euclid around 300 BC. This is especially awesome because Euclid didn't even have a concept of what a cosine is. How did he do it? Let's find out. If you haven't already, you should also see Euclid's proof of the Pythagorean theorem. Euclid proves cosine law separately for acute-angled and obtuse-angled triangles in propositions 12 and 13 of Book 2. For obtuse-angled triangles, Euclid makes this wordy statement. He then makes a similar statement for acute-angled triangles. Rather than trying to decode the confusing text, let's see the actual proof. We will start with the acute case, with acute triangle ABC. Conventionally, we have a way of naming the sides so that the side is the lower case of the opposite angle, so side A is opposite point A. That's what this version of the cosine law refers to. We could also label that side BC because it is the line connecting points B and C. Rather than calling A an angle, we can also refer to it as angle BAC, which makes it clear what we are referring to. First, we draw a line from point B that is perpendicular to the line segment AC. This intersects AC at some point, which we will call D. Note that D is not necessarily in the center of AC. So we've built a right-angled triangle, BCD. By the Pythagorean theorem, we can see that the square of BC is equal to the square of BD plus the square of CD. We also have another right-angled triangle in this figure, triangle ABD, so the square of BD in blue plus the square of AD in green adds to the square of AB in purple. So now we can see that the area of the purple square plus the red square equals the area of the green square plus the pink square. Now, notice that the square of AC can be broken down to a sum of the square of AD plus the square of CD plus two of these rectangles, which have dimensions AD by CD. Interestingly, this is just like expanding a binomial raised to the power of 2. So we can adjust our previous statement by adding in the green square and the two yellow rectangles. Thus, the purple square of AB and the yellow square of AC add up to the same area as the pink square of BC plus two green squares and two yellow rectangles, AD by CD. Because the green squares and yellow rectangles share a side length AD, we can combine them to make two light green rectangles. These rectangles have one side length AD, and the other side is the sum of AD and CD, so it is equal to AC. Thus, each of these light green rectangles has dimensions AD by AC. So now we can reiterate our previous statement as the sum of the squares AB and AC is equal to the square of BC plus 2 AD by AC rectangles. This is what Euclid was getting at in his statement of the cosine law. Euclid's statement seems complicated because Euclid tries to describe the light green rectangles, which we defined in the proof. Now we can convert this to the cosine law we are familiar with. The rectangle has sides AC and AD. AC is also one of the sides of the triangle, so that's simple enough. AD is part of this right-angled triangle. Using good old SOHCAHTOA, we know that the cosine of this angle, BAC, is the adjacent side over the hypotenuse, or AD over AB. Rearranging shows that side length AD equals AB times the cosine. We multiply both sides by AC to show that the area of the light green rectangle equals AC times AB times the cosine of BAC. Remember our geometric statement was that the area of the pink square plus two light green rectangles equals the area of the purple square plus the yellow square. So our equation is just a notation for writing that. We can convert it to the common notation to find that 2bc cos A plus A squared equals C squared plus B squared. It only takes elementary algebra to notice that this is equivalent to our original statement, A squared equals B squared plus C squared minus 2bc cos A. Because all of the angles in this triangle are acute, our proof works even if you use a different triangle or label the points in a different order. So, we have shown what was required to show. But hold on! What about obtuse angled triangles? Euclid deals with that in proposition 12. Euclid constructs this right-angled triangle instead, so that point D is outside the original triangle. He then makes some rectangles over here, and follows a very similar path to prove the cosine law again, but for obtuse angled triangles. Thus, we know that this law is true for any triangle, regardless of its angles. Thanks for watching! I hope you now understand how the cosine law was first proven by a guy who didn't know what cosine is. Now, don't be obtuse, click the like and subscribe buttons below. You know it's the right choice. You may have noticed that the Pythagorean theorem plays a big role in this proof. If you want to see Euclid's proof of the Pythagorean theorem, just click here. If you have comments on this video or suggestions for future videos, please leave them in the comments section below.